All right. Hello, students. This is Mr. Rich. Thank you for joining my live stream, or if you're watching this on the replay, I welcome you. And let me fix a few audio things here. All right, so stand by while I try to get this fixed. I think we got it. All right, I think that's going to work. All right, well, thank you, class, or I should say students. You're not my class. Maybe some of you who are watching this might be in my class, but at any rate, this is going to be a session tonight where we're going to review for AP Calculus. And a couple of weeks ago, I did a live stream where I talked about some of the concepts that you needed to know going into AP Calc AB, and kind of gave a broad overview of some of the things you might want to concentrate on this summer and review from your pre-calculus class. And today we're going to concentrate on one particular topic that you want to brush up on before you get started in calculus this fall. And that is the topic of trigonometry. So we're going to talk tonight about some broad trigonometry concepts. I'll work some example problems. We're going to talk about what are the trig ratios that you need to know. We're going to review special right triangles. So we'll go back a little bit into geometry because you do need to know your special right triangles. I'm also going to show you how those relate to the unit circle, right? So you need to go into AP Calc knowing your unit circle. You definitely need to know that. And it's something that, the unit circle is, I do see a lot of AP Calc students come in that don't know the unit circle as well as they should. And so it's something that on any test, you're not going to have a unit circle. You're not going to have a formula sheet for any trig identities. So we're going to talk about unit circle, how to memorize the unit circle. We'll talk about the graphs of trig functions, right? So you want to make a connection between the unit circle and sine and cosine and tangent, and how those relate to the graphs of those functions on the xy plane. And we'll also do some solving of trig equations and simplifying trig expressions using trig identities. So that's something that I want to go over tonight as well. So if your goal is to get a 5 on this AP exam next May, which I hope it is, right? If you're going into AP Calc, you want to go in and nail this thing. It may seem like an impossible task to get a 5. It is not. If you put forth the effort in your calculus class and you use the resources that your teacher makes available to you, there's no reason why you can't get a 5 on that AP exam. And your teacher, when you get into class, is going to go over what it's going to take, what in terms of percentages and scores, raw scores that it's going to be required to earn that 5. And you'll see that it definitely is a doable thing. Okay, so I'm going to share my screen, and we are going to jump right into it. Let's see if we can get this to work. All right, so you should see my screen right there. So there's the topics that we're going to cover tonight. We're going to start off by reviewing trig ratios, special right triangles, as I said earlier, unit circle, trig functions, solving trig equations, and then simplifying trig expressions. That's going to be the goal. Now, if you are watching live, you can put in any questions that you have into the chat. If you're in YouTube, I'll be able to see those. If you're watching this on the replay on YouTube, still, if you have a question or something that you're saying that doesn't make sense to you, go ahead and leave a comment, and I'll monitor that and try to give you a timely reply. So let's jump right in and let's talk about trig ratios. So let's do it this way. So the very first thing that I want to talk about are going to be trig ratios. So you need to go into this class, into your AP Calc class, knowing your trig ratios. And really, there's almost no way you can get through pre-calculus without knowing these basics. So you probably have memorized SOHCAHTOA, and yeah, so SOHCAHTOA. So is your sine ratio, opposite over hypotenuse. Cosine is your adjacent over hypotenuse. Tangent is your opposite over adjacent. You also need to know your reciprocal functions, right? So each one of these functions, sine, cosine, and tangent, they have their own reciprocal ratio. So the reciprocal of sine is cosecant. So cosecant is 1 over sine, which would mean then that cosecant would be hypotenuse, be the ratio of the hypotenuse divided by the opposite side from that angle. And secant is 1 over cosine, which would mean that secant is hypotenuse over adjacent, and cotangent's 1 over tangent, which means then that this would be adjacent over opposite. That's what cotangent is. So you want to know those going in. And of course, which side is adjacent and opposite depends on which angle of the triangle that you are referring to. Hypotenuse is always the side that's opposite the 90-degree angle. That never changes. But if I am talking about this angle right here, then this then becomes the opposite side. And this becomes the adjacent side. You can see, though, in this figure that we're talking about this angle. So that makes this side the opposite, and the one next to it the adjacent side, and the hypotenuse is always the hypotenuse. All right, so trig ratios are important. Now, let's talk a little bit about special right triangles. I do a lot of work with students in prepping for the SAT and the ACT, and I'm always surprised, even students that are scoring in the upper 20s, low 30s, a lot of them have forgotten special right triangle ratios. And it is something definitely you want to know in AP Calc. So let's review that. Now, this doesn't look too much like a 45, 45, 90 right here, but let's pretend that it is. I'm going to mark this and say that those two sides are the same length. They are congruent, and that this is a right angle. So that makes this a 45, 45, 90. Those two angles would be congruent. Therefore, they're 45-degree angles. Now, what we know from our geometry class is that if my legs are represented by the variable x, then it means that the hypotenuse is going to be square root of 2 times whatever the length of the leg is, x. So if I'm going from the leg to the hypotenuse, multiply by root 2. If I'm going from the hypotenuse back to the leg of a 45, 45, 90, I would divide by the square root of 2. Right now, you probably would say, well, gee, I could figure that out with Pythagorean Theorem. True, but we want to be able to do things efficiently and quickly, and this is something that is going to come in handy in your calculus class as it pertains to trigonometry. Let's talk a little bit about the 30, 60, 90 triangle. If that's a right angle, and this angle is 60 degrees, and this angle is 30 degrees, then, and how did I know that? Well, I know that the shortest leg is going to be opposite the 30-degree angle. Now, what I'm going to do is I'm going to label the shortest leg of this 30, 60, 90 with the variable x. And the other two sides are going to be just a multiplier times that short side x. And the hypotenuse is always going to be twice the length of that short leg. It's going to be 2x. And the side that's opposite the 60 degree, the longer of the two legs, that's going to be root 3 times the short leg of x. That is the relationship. And again, you could use trigonometry to get those other three sides, but you don't want to. Right? You want to know these relationships on these two special right triangles. Now let's work one example problem. I don't want to spend a lot of time on this. I'm only going to really work one example problem. So let's take a look at this. So suppose I want to find the area of an equilateral triangle with sides of 4 feet. So if it's an equilateral triangle, then of course these 3 sides are all congruent, and that these would all be 60-degree angles. And I want to find the area of this equilateral triangle. So I know that the area of a triangle is going to be 1/2 base times height. And I know that the length of each of these sides is going to be 4. Now, what I'm going to do, though, is I'm going to call this bottom length, the bottom side of this triangle, to be my base. And if that's true, then the height is going to be this distance right here. But when I drop that perpendicular from this vertex of the triangle down to the base and drop down that perpendicular, that does become then the height of the triangle. Now, what's the length of that? Well, it's going to be pretty easy because I know 30, 60, 90 triangles. I know that this is going to be a 30-degree angle right here. This is 60, so I'm now working with a 30, 60, 90 triangle. And that would mean that this distance right here is going to be 1/2 of 4, or 2. So now I know then that this height here is going to be, and this is the shorter leg here, right? Because this is opposite the 30-degree angle. So that means that this height here is √3 times 2. √3 times 2. So when I go back and calculate my area, I know that it's going to be 1/2. My base is 4. The height is going to be √3 times 2. And then I can calculate my area. This 1/2 is going to cancel out that 2, and I'm left with an area of 4 times the square root of 3. So I didn't really have to use any trigonometry to get that height because I know the relationship of the sides of a 30, 60, 90 triangle, so it makes it much, much faster. All right, so that's one thing that you want to brush up on if you need to. Now, I want to talk a little bit about the unit circle. So let's take a look at generally what is a unit circle. This is a unit circle. Now you may say, well, that's not kind of what I memorized. It doesn't really look like the thing that I memorized, the unit circle. Well, maybe so, but I just want to go over the idea of the unit circle. So in the XY plane is where the unit circle exists. You mustn't forget that. And it is a circle of a radius of 1, because if my radius is 1 unit in length, then that would make each one of these points here as shown. This would be 1, 0, 0, 1, -1, 0, 0, -1. Now, what I want to do, though, is I want to consider this. Let's just take a generic point that is on the unit circle, and I'm going to draw a radius up to that point. I'm going to call this point x, y, and I'm going to drop a perpendicular down here to the x-axis and draw myself a right triangle. Now, this would be, if this coordinate of the coordinates of this point are x, y, that means that this distance here is literally x, and that this distance here is y, because that's why I would call that x, y. And now, if I'm going to call this angle here theta, and I were to write what sine theta is, I know that the ratio in a right triangle for sine of an angle is the opposite side length divided by the hypotenuse. Well, in this case, the sine is the length y. But what is the hypotenuse? Well, the hypotenuse we already established was length 1, so it's 1 over y over 1. So we can say then that sine theta is simply whatever the y coordinate is in our unit circle. Likewise, I can write cosine of that angle as being the ratio of the adjacent length of the triangle divided by the hypotenuse. And the adjacent length is x over the hypotenuse length 1. So cosine theta is just simply equal to x. So that means that any point on this unit circle really can be written, instead of x comma y, it can be written as cosine theta comma sine theta by just simply substituting for x being cosine theta and y over here being sine theta. All right, and so that is the idea of a unit circle, a circle of radius 1 superimposed on the xy plane, with the center of that circle being at the origin 0, 0. All right, so what does that mean though? Well, let's do a couple of problems here on a generic unit circle. So here I've got two problems, and I'm saying that I have a point on the unit circle and I need to find a missing coordinate. So suppose that on my unit circle above, there was a point 7/25 comma y, and y is greater than 0. And I need to find out what that y would be if that point is on the unit circle. So let's try to establish what this answer would be. So I'm going to draw my unit circle. We'll just sketch one right here. And what we're going to do, 7/25 would mean that I'm coming out. I'm just going to call this a point here, 7/25 y. So that would mean then my hypotenuse is 1. This distance here would be 7/25. And I need to find out what the y coordinate is, like that. Well, a couple of ways I could do it, but I'm just going to go ahead and use the Pythagorean theorem, because I know that this would be y squared plus 7/25 squared would have to be equal to 1 squared. All right, so what would that mean? Well, that would mean then that y squared that I'm looking for here would be 1 minus, this would be 7 squared, 1 minus 49 over 625. Now I'm going to pull up my calculator here, and let's make sure that I've got that right. So we'll do 25 times 25. Try that again, 25 times 25. 25. So let's do that. So that's going to be 625 over 625 minus 49 over 625. And we'll do that on the calculator, right? So I'm going to take 625 minus 49, and I get 576. So this is 576 over 625. That's what y squared is. When I solve that for y, then I get y is equal to either plus or minus the square root of 576 over 625. Well, we know what that's going to be, right? Because this would be 15. And if you take the square root of 576, which we will go ahead and do. So let's try that. Square root 576. Whoops, try that again. Square root 576 is 24. So no surprise there. That ends up being 14 over 5. Or 24. Sorry, that's 25. This is 24 over 25. All right, so that, and now it could be a plus or minus, right? But we're talking about y being positive, so this coordinate has to be 24/25. So that means that if it's on the unit circle and the x value is 7/25, then this would have to be a positive 24/25. like that. So that's the idea of the unit circle. I'm not going to work this one. I'm going to move on. Now, what do we do then with the unit circle, right? So taking it a step further, what we really are interested in, and you worked with this in your pre-calculus class, is we are interested in standard angles of 30, 45, 60, and then multiples all the way around the triangle, all the way around the circle, I should say. So let's move this thing over a little bit. Okay. There we go. And you can see here that we've got, in the first quadrant over here, I've got angles of 30, 45, and 60. Now, I do want to tie this back to the unit circle, right? Where do these numbers even come from? They do come from the unit circle. If you take this first angle, which is 30 degrees marked on our unit circle, and you drop a perpendicular down from the point that's on the unit circle down to the x-axis, you do create a 30, 60, 90 triangle. And I know that the hypotenuse is length 1 because of the fact that it's a unit circle out here. So that length is 1. Well, if I use my relationships from the 30, 60, 90 to go from the hypotenuse to the shortest leg opposite the 30, I cut that in half and I get a 1/2. But then to get the longer leg, I take the short leg times √3. So that becomes 1/2 times √3, or √3/2. And that's where this coordinate comes from. All right, so the x coordinate is √3/2, and the y coordinate is 1/2. When you go to the 60-degree angle, everything just kind of flips around, because now we're talking about this angle here being 60 degrees, and this one on the top is now 30 degrees. And this is still a hypotenuse of 1, but now my short leg is this one down here that's along the x-axis. That's going to be now a 1/2, and then 1/2 times √3 gives me √3/2. And that's why you have a flip-flop right here between 30, 60, and 90. Between 30 and 60 in that first quadrant, those x and y coordinates flip. All right, now you can see too that if we go with the 45-degree angle here in the first quadrant and we make ourselves a right triangle with a hypotenuse of 1, we know that I would, to go from the hypotenuse to the legs of a 45, 45, 90, I divide by square root of 2. So this becomes 1 over the square root of 2. I rationalize that by multiplying by √2 over √2, and I get √2 over the square root of 4, or 2. And that, again, is why I've got √2 over 2 as my coordinates on the unit circle. So your job coming into AP Calc is to know your special right triangles and know all of these coordinates around the unit circle in all 4 quadrants. Now, if you know the first quadrant unit circle, you can pretty well get the other ones. You can see these dashed lines are coming across to show you kind of the symmetry that's involved here. That this point, for example, and this point, they really are the same coordinates. The only thing that has changed is that it was reflected across the y-axis. So the x coordinate is a negative 1/2. But what I recommend is that you have a way to immediately, when someone says, hey, 210 degrees, what's sine and cosine, you should within just a few seconds be able to visualize or use some sort of trick that your teacher has taught you to know what the coordinates are, so that you know the sine and cosine. Now, the one that I use, and it's one that I use, mentally, I'll show this to you on the unit circle, but I just follow a pattern that goes from the top of the unit circle along the y-axis all the way down on each side, and then from the bottom I go up, and I visualize the following. So if I were to show you going back to this unit circle here, let's try it this way. Here we go. So what I want to show you here, that what I do when I visualize this is I start up at the top, and as I go down, I know that this thing goes 1, 2, 3 in the numerators and back 1, 2, 3 in the numerators. And it does it in both directions. Okay, 1, 2, 3, and then climbing back 1, 2, 3. So I visualize that. So when I visualize the unit circle, I'm visualizing that pattern. I know that all the denominators have 2, and I know that all the numerators are square rooted. Those 1, 2, 3s coming down and 1, 2, 3s coming back up, they're all square rooted. And of course, the square root of 1 is 1, so I don't have a square root on the 1, obviously. And I also know that my x values over in the second quadrant are negative while the y values are positive. So I keep track of that as well. But my point is, whatever method you use, you have to have a system for being able to quickly and accurately obtain the coordinates along the outside of the unit circle. That's just something that's going to be expected. And if you're looking for that 5, right, you don't want to be tripped up for not knowing some of the trig functions. Now, it's not as though, just making a comment here about trigonometry and AP Calc. They're not so much interested in testing you on things that you learned in pre-calculus. It's just that when you learn calculus, you have to be able to work calculus on many different types of functions that you've worked with. Polynomials, rational functions, trigonometric functions, many different types of functions. You're going to be doing calculus on those functions. So trig functions are like any other function. You have to know how to work with them. And if you're going to do it well in calculus, you can't be stumbling over the basics of what are the trig functions and what are the values for different angles of trig functions in a right triangle. Okay, so you definitely want to have that down when you go into class this fall. All right, let's go back. One thing I think maybe would be a good idea to cover is let's talk about converting between degrees and radians, because on the unit circle, you do also, I failed to mention this, not only do you want to know the ordered pairs, but you also want to know the degrees and the radians all the way around the unit circle. And there's a pattern to that as well. I'm not going to go into that, but you need to, and the way that I do it is this, class, when I'm considering what is sine of 330, for example, right? If I need to know what's sine of 330, I'm visualizing where 330 is on this XY plane, right? I'm visualizing that my 330 is out here. And then I'm visualizing what the X and Y coordinates are out here. So then I know that my Y coordinate is going to be my sine. And so I'm able to say that that's going to be a -1/2. All right. Now, as far as when it comes to radians, because you'll mostly be using radians in Calc AB as it pertains to any of the trig functions that you're working with. So you want to be able to know where the radian angles are, what quadrant they're in, and so forth. So definitely you want to have a pattern so that you know where 7 pi over 6 is. And again, I'm not going to go too much into that. But just refresh yourself on those. And let's not forget that when we're talking about tangent of theta, we're basically using the trig identity that tangent is sine over cosine. But I know that sine is the y coordinate and that cosine is the x coordinate. So really, although my tangent function is not listed here on the unit circle, I obtain it by dividing the y coordinate by the x coordinate. And since all the denominators are 2, I only need to work with the numerators. So when we say, gee, what is tangent of 5 pi over 3 down in the fourth quadrant? Well, here happens to be 5 pi over 3, and this is a -√3 over 1, right? It's my y numerator over my x numerator. So this is just a negative square root of 3. And then the reciprocal functions are easy because I can just flip those. And I know that this would be a negative 1 over root 3 if I was looking for cotangent. Another thing to remember is your teacher in pre-calc probably showed you that a good thing to remember is all students take calculus, ASTC, which tells you which trig functions are positive in which quadrant. So sine and its reciprocal cosecant are positive in the second quadrant, tangent and its reciprocal cotangent, positive in the third quadrant, cosine and its reciprocal secant, positive in the fourth quadrant. All trig functions in the first quadrant happen to be have positive values. Let's talk about converting between degrees and radians. And what we do when we do this conversion, if you remember, is we just realize that, pi radians is equivalent to 180 degrees, which would mean then that if I set up a ratio of pi radians over 180 degrees, since those are equivalent measurements, they are equal to unity, to the number 1, which means I can multiply any measurement by that ratio and not change it or make it bigger or smaller, but just convert the units. So, and likewise, then 180 degrees over pi radians is also unity. So that means that if I were looking at some non-standard angles, like let's just suppose we were looking at 20 degrees, and I wanted to convert 20 degrees into an equivalent number of radians. Well, what I do is I'm going to take 20 degrees over 1, and I'm going to multiply it by this ratio. Now, the ratio that I'm going to use is this one because I want to cancel the degrees. So I want to put pi radians over 180 degrees. My degree units are going to cancel. 20 goes into 189 times, so I get pi over 9 radians. Okay. And if you're converting the other way, going from radians into degrees, then you would just be multiplying by 180 degrees over pi radians. So good practice would be to fill in the unit circle. I know that in many pre-calculus classes, teachers so much want you to be able to memorize this that they will give quizzes where they'll give you maybe 60 seconds to completely fill in the unit circle. So definitely get some practice on the unit circle and make sure you've got that memorized. Now, I want to talk a little bit about trig functions themselves. You should be able to make a connection between what's happening on the unit circle and then the graphs of the trig functions as a function of the trig function y equals sine theta, where you're plotting the sine of an angle versus the angles over the unit circle. So in other words, I know that sine starts off at 0. Sine of 0 is 0. When I go up to 90 degrees or pi over 2 radians, then my sine value goes to 1. That's reflected, of course, on the unit circle up here, right? When I go to 90 degrees, my y coordinate is a 1. Okay, so sine of 90 degrees is 1. And that's the pattern that you see. And these are the quadrants, right, that are showing you what's happening here. So that's why in the first and second quadrant, sine's positive. But when I go to the third and fourth quadrant, sine values are all negative in those two quadrants because you're down below the x-axis in negative values. Now, when I tell my students, that when I'm dealing with angles that are on the axes of the unit circle at the 90-degree multiples, I visualize the function itself, right? So when I'm thinking sine of 180, I'm picturing that point, and I know sine of 180 is 0, or sine of 270 is -1. So it's a good idea, right? To be able to use visually in your mind anyways, these trig functions, the graphs of the trig functions to get values off of the unit circle. Cosine is really just the sine function, but shifted 90 degrees to the left. So it starts off at 0 degrees. It starts off at a value of 1, which on the unit circle is reflected by this point right here. When you are at 0 degrees of rotation, the x-coordinate is a 1. So cosine of 0 is 1. Here's tangent and cotangent. Not a bad idea to remember these graphs. Right, one of the big differences between sine and cosine is the fact that the period of tangent and cotangent is only 180 degrees versus 360 degrees. But notice that when we're going through the first or through the entire unit circle from 0 out here to 2 pi, there are 2 places in the unit circle, one at pi over 2 and one at 3 pi over 2, where tangent does not exist, right? Because I would be dividing by 0. So pi over 2, there's a vertical asymptote for tangent at pi over 2, again, reflected on the unit circle, because when we go to a 90-degree rotation, tangent is y divided by x. Well, that would be 1 divided by 0, which is undefined. So that's why tangent is not defined at both 90 degrees, or pi over 2 radians, and also 270 degrees, or 3 pi over 2, because the ratio of y divided by x is undefined. All right, that is about all that I really wanted to say about the graphs of the trig functions. I also put in here the graphs for the reciprocal of sine and cosine, cosecant, which is the reciprocal of sine. And, the thing about this is wherever you've got these vertical asymptotes on the secant and cosecant functions, that's where its reciprocal function would be passing through the x-axis. And wherever it has a relative min or max, that's also where the reciprocal function is touching it. So I kind of know, I can visualize this and know that this is a cosecant graph, because I kind of plot the function, its reciprocal function, that's kind of going in between here. And I can see that that's a sine function, which tells me that's the reciprocal cosecant. All right. Also, not a bad idea to know your inverse trig functions, because we will be doing calculus involving inverse trig functions. And not going to spend a lot of time on this one either, but just to say that when we're dealing with the inverse sine function, or the arc sine function, we're really only dealing with the sine function from negative pi over 2 to pi over 2. So its domain is going to be negative 1 to 1 on both sine and cosine, because that is the range, right, on its reciprocal, the sine function. So just to remind you, let's go back up here to the graph of sine. If we stretch this function back this way, what we do, so that we make sure that the inverse function is indeed a function and that it's 1 to 1, we really only consider from pi over 2 to negative pi over 2. So we're really working with this part of the sine function when we're talking about arc sine. That's why we kind of restrict the domain here to be negative pi over 2 to pi over 2. So that's what becomes the range then here, negative pi over 2 to pi over 2, and it stretches from negative 1 to 1. All right, so these are those are the reciprocal, not reciprocal, but the arc functions for sine, cosine, and tangent. Now, let's talk a little bit about solving trig equations. And in order to do that, though, let's talk about the trig identities, right? One of the most challenging parts, I think, of pre-calculus, at least I have found working with students, and I taught it for a few years as well, is trig identities, right? The simplifying of trig expressions, solving trig equations, proving trig identities can be challenging. And you probably had maybe a full page of trig identities. Now, not all of those trig identities are you really going to be using in AP Calc. I'm just going to be honest with you that you can get by in most cases with just knowing your reciprocal identities and your tangent and cotangent, right? Those two right there, as well as the Pythagorean identities. That's going to be 90% of what you need when you're dealing with trig functions in AP Calc. Now, do you need to know addition and subtraction? Yeah, I definitely would say these are things I would definitely memorize these as well. Okay, it's possible that those can come up, especially the double angle. I would say the double angle formulas are probably more common than even the addition and subtraction formulas. So that's what I would go with there. Now, I don't know if your teacher told you, right, but as long as you remember this function right here, these other two Pythagorean identities fall right into place, because if you divide everything by sine squared here, right, you're going to get another identity, because this is a 1, this is cotangent squared, and what is 1 over sine squared but cosecant squared theta. Right, so that's what gets you that. Or if you divide everything through by cosine squared, you'll get the other identity. Okay, so I just want to throw that out to you, because I do see that students, almost all students I work with, have that thing memorized, but they somehow don't have these memorized. But these can easily be obtained, as I just showed you. Now, let's do some practice problems, some things that you need to be able to do, right? Let's start off with solving trig equations, right? I need to be able to take an equation that has some trigonometric functions in it, and I need to be able to solve it for theta. So let's see how we would do that. Now, here I've got 1 plus cosine 2 theta equals cosine theta. And I don't want to have a different argument in my cosine. So I want to get rid of that cosine 2 theta. And I'm going to use this identity here that's going to put it in terms of cosine, right? Not only do I want to get rid of the cosine 2 theta, I don't want the 2 theta, but I also want to leave it in terms of cosine. I have 3 options on cosine 2 theta. I got one that involves cosine squared, one that's sine squared, and one that is both of them. So I'm going to use the one that converts this to cosine squared. So my equation would become 1 plus 2 cosine squared theta minus 1 is equal to cosine theta. Now, that makes it really a quadratic type function, because I've got cosine theta and I got cosine squared theta. So I'm going to treat this as though it was a quadratic equation, and I'm going to get all my terms on one side. Now, the 1 and the minus 1 are going to cancel to 0, but I'm still going to bring this 2 cosine squared theta, leave it on the left side, and I'm going to bring the cosine theta over as negative cosine theta, and that would be equal to 0, since these two terms are going to add up to 0. Now, what I'm going to do is I'm going to factor this, right? I'm going to factor the greatest common factor of cosine theta out, leaving me 2 cosine theta minus 1 equals 0. And anytime that I am solving a quadratic equation and I end up factoring it, I'm going to use my zero product rule that says that if I've got two things multiplied that are equal to 0, then either one of them has to be 0. So I solve this by saying cosine theta is equal to 0, and 2 cosine theta minus 1 is equal to 0, right? It's basically an or. Right? My equation that I'm solving is going to be true when either of those two equations are true. Now, I am here trying to find all solutions, not just solutions that are in the unit circle from 0 to 2 pi. So what I'm going to do is say, okay, well, when is cosine 0? Well, what I'm really doing here is I'm really taking the arc cosine on both sides of this equation. So let's not forget that. What I'm really doing from an algebra standpoint is I am taking the arc cosine on both sides of this equation. The arc cosine of cosine is theta, leaves me just the argument theta. And now I've got theta is the arc cosine of 0. Now let's consider within the unit circle, when is cosine equal to 0? Well, there's going to be two angles where that's going to happen. So theta is going to be, cosine is 0 at pi over 2, and also at 3 pi over 2. Now, let's go over here. We'll come back to that in just a second. So, because remember, I'm trying to find all solutions. So let's go over here. I'm going to solve this by adding 1 to both sides. I'm going to divide both sides by 2. And then I'm going to take the arc cosine on both sides. When I take the arc cosine on the left, that leaves me theta, and this is arc cosine of 1/2. Now, let's consider, when do I have, for what angle do I have a cosine of that angle of 1/2? Well, that's going to be, well, where's that going to be? If you go to your unit circle, that's going to be, let's go take a look at it. Where do I have cosine equal to 1/2? Right, so we're up here. Right, here is cosine being 1/2. That's pi over 3. And it's also going to be true down here at 5 pi over 3. So we're going to give those two answers because I know in the unit circle, that's when cosine theta is equal to a positive 1/2 pi over 3, 5 pi over 3. Now, but since I want to give answers, all answers, I'm going to use multiples using a multiplier of n as an integer. Now, this means that pi over 2 and 3 pi over 2, and the next one is going to be at pi over 2 plus 2 pi. So this solution here is going to be pi over 2 plus all multiples of pi, or 180 degrees. That's why I went from pi over 2 to 3 pi over 2, right? Because I know up here at 90 degrees, cosine is going to be 0. And then I rotate another 180 degrees down here at 3 pi over 2. And then if I go another 180 degrees, right, it's going to be again back here. So every 180 degrees or every pi radians, I'm going to have a solution to that equation. Over here, though, I have to do this a little bit different because it's not just multiples of pi. It's going to be pi over 3 and every rotation after pi over 3. So these two solutions, I'm going to write them like this. This is going to be pi over 3 plus 2 pi n. And theta is 5 pi over 3 plus 2 pi n, where n is any integer, positive or negative or 0. Okay, so those are my solutions right here. All solutions to this I just found. It's going to be theta is pi over 2 plus n times pi. Also, these are my other solutions. So that's an example of solving a trig equation using your unit circle. Now, these next ones that I'm going to work are where I'm finding all solutions confined between 0 and 2 pi, 0 inclusive, 2 pi exclusive, just within my unit circle. So I don't need to consider solutions outside of the unit circle. Well, I'm going to solve this one's pretty straightforward. I'm going to isolate my sine. So I'm going to add 1 to both sides. I'm going to divide both sides by 2. And then I'm going to take the arc sine of both sides. So theta is equal to the arc sine of 1/2. And then I have to consider on my unit circle, when is sine equal to 1/2? Well, I know that I have to be in what quadrant? So I'm going to be in the first and second quadrant. That's where sine is going to be positive. Okay. And if I do this in my mind, but I'm drawing it out for you here so that you can see kind of what I'm picturing in my mind. I know in the first quadrant, remember I said 1, 2, 3, 1, 2, 3, right? Meaning 1/2, and all these denominators are 2. I would be square rooting the numerators like that. I know that my sine is my y coordinate, and so it's over here, right? This is the angle that I'm looking for, 1/2. So that's going to be pi over 6. But also it's going to be the same value over here, which should be 5 pi over 6. So I have two solutions between 0 and 2 pi, where sine is equal to 1/2. That's at pi over 6 and 5 pi over 6. All right, let's keep going here. Let's try another one. Solving this for theta. So I'm going to isolate my sine squared first. I'm going to add 2 to both sides. I'm going to divide by 4 and reduce. So now I've got sine squared theta is equal to 1/2. I'm going to square root both sides. So that's going to give me sine theta is equal to the square root of 1/2, positive or negative. Well, let's go a little bit further. That would mean that this is plus or minus 1 over the square root of 2, because don't forget, this would be the square root of 1 over the square root of 2, plus or minus, which is plus or minus 1 over the square root of 2. When I rationalize this, I get plus or minus root 2 over 2. So then, I basically, at this point, I'm at sine theta is equal to plus or minus the square root of 2 over 2, taking the arc sine on both sides. So theta is arc sine of plus or minus root 2 over 2. So what angles have sine of plus or minus root 2 over 2? That's going to be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So those are my 4 solutions to that particular trig equation. All right, I think what we'll do, let's do a little bit more here on simplifying trig equations. And I think we'll call it a night on that. So let's take a look at simplifying trig. Now, you know, when do you have to do this? When is that going to come up on the, when is that going to come up in AP? So a lot of times when you're working with trig equations, you may come up with a solution after you've done some work, some calculus on a particular equation, and you need to match it maybe to a multiple choice question. And that may require you to do some manipulations or simplification of your answer to match one of the answers in the multiple choice. So knowing your trig identities is going to be very helpful to do that. These that I've chosen, I think, are pretty simple, but let's see what happens here. So let's go back to the screen here. And what I'm going to do here is I'm going to, in a case like this where I've got mixtures of tangents and sines and cosines and such, I'm going to get everything in terms of sine and cosine. So I'm going to call this sine squared x over cosine squared x. There's a sine x, and I'm going to change this into 1 over sine x. All right. Well, that's interesting because this is just going to simplify to a 1. And maybe I didn't need to change that. Maybe just tangent squared x plus 1. All right. Well, what does that simplify to? Well, if you go back to the trig identities that I was showing you on your Pythagorean identities, 1 plus tangent squared theta is secant squared right here. So we'll come down, and that basically is going to be the end of that problem, because this is going to be secant squared x. This one here, I'm going to convert to everything into sines and cosines. So secant is 1 over cosine x. That would be times sine x over 1. And cotangent is cosine x over sine x. So sine x over sine x is 1. Cosine x over cosine x is 1. My answer is 1. Not too bad. And let's do one more here. Sine x times cosecant x minus sine x. I don't think that's going to be much of a problem to simplify this. I'm going to go ahead and distribute my sine x. So this is going to be sine x cosecant x minus sine squared x. Well, but cosecant x is 1 over sine x. Sine x times 1 over sine x is 1. 1 minus sine squared x. And that's going to be cosine squared x by using the Pythagorean identity. And that's my simplified form. Right. Now, if you think back about precalc and what gave you maybe the most trouble or some of the really challenging trig identity problems, it's not really something that you see on Calc AB, right? They're not here to say, hey, let's see if this person really remembers the hardest problems in pre-calculus. That's not really the intent of the College Board. They want you to be able to do calculus with trig functions, right? So they're not going to get you bogged down in like the most challenging problem when it comes to trigonometric identities. But you do need to be able to use them and manipulate them and take equations to solve for a variable. You've got to be able to manipulate and transform expressions, trig expressions, using the identities as they come up. And you need to know your unit circle. Now, when I last was here 2 weeks ago, I did post to my live stream in YouTube down in the description a couple of pretests, right? So I think the best thing for you to do is do a pretest of concepts that you learned about in your pre-calculus class to see what you need to brush up on. So in the description for this live stream, you'll see the same links there. There were 2 practice tests or pre-tests that I gave you to get you ready for AP Calculus. So click on those hyperlinks. You can get the test. I gave you the answer key to both of them, so they're also hyperlinked. And then you'll have a little bit better idea maybe of what you want to focus on. So next week, I'm going to do another live stream on another concept. I don't remember which one it was. It might be rational functions, but I'll get the post up early this week so you can check those out. And hey, Elliot, I don't know if you're still here. I didn't see your comment, but it was pretty awesome. I just got back from a cruise. Elliot was asking me about how my cruise was. We were on the Carnival Mardi Gras on a 7-day cruise, and it was pretty awesome. But now back to work. And I don't have a Discord, Elliot, if you're still watching. So no Discord. Maybe I'll get one, but anyways. But as I was saying, so each Sunday night for the rest of the summer, I'm going to tackle one topic from pre-calculus and kind of review it and work some problems for you, and then see if you have any questions. Again, so if you thought this video was helpful, if you would hit the like, that would be awesome. And feel free to subscribe to my channel, and that way you'll get notified every time I post some new content. So now that I'm back from vacation, I'll be posting some additional content too on a weekly basis, as well as these live streams. All right, so thanks for watching, and I will see you all next week. Bye.